So hello everyone, this is lecture 11 for the thermal physics. In the last lecture we have studied about the first law of thermodynamics and we studied that how can we apply that law on the different processes. Now today we'll see that some kind of question can be framed or they are asked in the previous years. So it was asked in the TIFR 2022. So there is this tire which is at the means first let me read this. A bicycle tire is pumped with air to an internal pressure at 6 atmospheric at 20 degree at which it suddenly burst, assuming the external pressure to be 1 atm and the subsequent sudden expansion to be adiabatic. The temperature immediately after the burst is approximately. So there is this your tire and it is at 6 atm pressure and temperature 20 degree. Now it suddenly burst and the final pressure becomes 1 atm and you need to find the final temperature. So the process is adiabatic. So you know what formula you can apply. This condition is valid here and inside the tire this gas is simply oxygen or nitrogen, it can be anything, and both are the diatomic gases. So you know the gamma for them. Gamma for the diatomic gas is 7 upon 5. So just substitute the value here. T1 is 20 degree and means just change it into the Kelvin, and P1 is 6 and then P2 will be 1 and you need to find the T2. So all variables, only the one is T2 is remaining, so you can find the T2 from here. The answer will be minus 97.41. Now there is a similar question asked like this. So this question is same to like this. A thermally isolated container stores N2 gas at 27.24 degree at 1 atm pressure. Suddenly the pressure of the gas is increased to 2 atm. Assuming N2 to behave as an ideal gas, estimate the change in the temperature of gas in degree Celsius. So again N2, so you will use gamma the same value, and the T1 is this and P1 is this. T2 becomes 2 atm, so you need to find the P2 is this, so you need to find the T2, so you will use the same relation and you can find. A gaseous system enclosed in an adiabatic container is in equilibrium at pressure P1 and volume V1. Work is done on the system in a quasi-static manner. Quasi-static manner is that manner in which at every state the system will remain in equilibrium. That is a very slow process. Quasi-static manner due to which the pressure and volume change to the P2 V2 respectively in the final equilibrium state. At every instant the pressure and the volume obey the condition PV gamma equal to constant, where gamma is nothing but Cp over Cv and C is a constant. If the work done is 0, then identify the correct statement. So in the adiabatic process what is the work done formula is 1 upon gamma minus 1 P1 V1 minus P2 V2. So this work done is 0. So this term will be 0 and P1 V1 equal to P2 V2. So this will be your answer. Next question is 1 mole of an ideal monoatomic gas at pressure P, volume V and temperature T is expanded isothermally to volume 4V. Thereafter, the gas is heated isochorically at constant volume till its pressure becomes P. If R is a gas constant, the total heat transfer in the process in the units of RT is. So there are two processes involved. First is isothermal process, and we are seeing the changes. Volume will changes from V to 4V. So isothermal expansion V to 4V, then pressure will change to P upon 4. You can find that using relation PV equal to constant because T is constant in isothermally. So P will become P by 4, V is 4V. So these are the two states. Now isothermal expansion will give you work this. In that case, the internal energy changes 0. So Q1 equal to W1. That will be nRT log final volume divided by initial volume. So 4V upon V. So this will be your work done. And this is your heat first in the first process. In the second process, now you heated isochorically. Means the volume is remaining constant. So there will be no work done there. So whatever change will give you the internal energy. So isochoric heating means there will be volume is constant, so pressure is changing to P by 4 to P till its pressure becomes P. So P by 4 to P and T is changing from T to 4T. You can find the using the relation PV equal to nRT. So V is constant, so P is just relating with the T. So P is becoming 4 times, so T is becoming 4 times. So that's how you can relate. Now here here there is no work done when there is volume is constant, so only change or the heat is transferred will be change in the internal energy. So when the process is at constant volume, so that's how you find the internal energy change. The formula is NCV delta T. So delta T is 40 minus T and CV you can find it is a monoatomic gas, so 3 by 2 R. So this will be your heat exchange in the second process. So total heat transfer will be Q1 plus Q2 and this will be your answer. Next is our diatomic gas undergoes adiabatic expansion against the piston of a cylinder. So adiabatic expansion is here. So in the adiabatic expansion, that there is no heat exchange. So whatever expansion is there, it will result to the temperature decrement, decrease in the temperature. So as a result, the T of the gas drops from the 1150 Kelvin to 400 Kelvin. The number of moles of the gas required to obtain this amount of work from the expansion is. So just use the adiabatic for work formula and just put the value of work here, and gamma you already know, this is the diatomic gas, so it will be 7.5 and then R, you know, 8.3, and T1 T2, so T1 is greater, that is 1150 minus 400, so you can find the value of N, that will be 0.1475. Next question is, an ideal gas undergoes an isothermal expansion along a path AB. So this plot was given. So there is this process, 5 processes are there: A to B isothermal expansion, B to C adiabatic expansion, C to D, this is the isobaric process, means this is a constant pressure. Here it is P, here it is V. So this is the isobaric process, C to D, and D to E it is isothermal compression, and E to A it is the adiabatic compression. So these 5 processes are given, and we need to find the change in the internal energy along the CD. Means, let's study the question. An ideal gas undergoes an isothermal expansion along a path AB, adiabatic expansion along BC, isobaric compression along CD, isothermal compression along DE, and the adiabatic compression along EA. As shown in the figure, the work done by the gas along the process BC is 10 joule, and the change in the internal energy along the process EA is 16 joule. The absolute value of the change in the internal energy along the process CD is. So see, it is given that change in the work done by the gas along the process BC is 10 joule. So work done along this is 10 joule. So first let's see in the AB, this is the isothermal process, so internal energy change will be 0, and along BC we know it is adiabatic, so dQ will be 0. So whatever, we can find out internal energy change, that will be minus dW, and dW is positive, so it is 10 joule, so internal energy change will be negative, minus 10 joule. Now along CD we need to find the internal energy change, so let's put it as question mark. Now D to E it is an isothermal compression, so du will be 0, and along EA we are having adiabatic compression, so here it will be du equal to 16 joule, that will be the work done given here, the 16 joule. Now this is a negative work done, so minus dW will give you positive value, that is 16 joule. Now you know this is a cyclic process, so overall change in the internal energy will be 0. So let's take the sum of all of them, and we can find along the CD, then it will give you minus 6 joule. So there will be decrement in the internal energy along the CD. Now let's see the next question. The equation of state for 1 mole of a non-ideal gas is given by this: PV equal to A1 plus B upon V, where the coefficient A and B are temperature dependent. If the volume changes from V1 to V2 in an isothermal process, the work done by the gases. So it is A and B are depending on temperature, means they are now constant because temperature is constant, isothermal process. To find the work done, we know this is the formula PdV. So we just find this expression in terms of the P. So P equal to 1 upon V, A1 plus B upon V. So just take these, means it will be A upon V and B upon V square. Take the integral and solve them, and you will get your work done. So this is the simple formula. Always apply this for the work done. Next is, consider a monatomic ideal gas operating in a closed cycle as shown in the PV diagram. So this diagram was given. So this is the monatomic ideal gas operating, means A to B it is expanding adiabatically, given adiabatically. We need to find the ratio P1 over P2. So it is adiabatic process, so we know the formula PV gamma equal to constant. So it is given in terms of P and V. So P1 V1 equal to P1 V1 gamma equal to P2 V2 gamma. So V1 is 3 V1, and this second is V1. So you can just apply this formula and you can find the relation. That will be this. This question is a little bit interesting, so we'll focus more on this. A hollow cylinder closed at both ends, means first you must see this. There is this adiabatic container, means isothermal isolated container where the heat can't be exchanged outside, and there is this disk, means there will be n cells framed by the n-1 disk, means there will be four different cells when there is 3 disks. So that's how for n cells you need to have n-1 disks. Now there is this first disk is adiabatic disk, means no heat can be exchanged from here to here, but all other disks will be dithermal, means heat can be exchanged. So this will be like this. So initially there was in every container you have the volume V0, means let's study the question now. A hollow cylinder closed at both ends with adiabatic walls is divided into n equal cells C1, C2, Cn using this D1, D2, Dn-1. The discs can slide freely without friction, means this can be freely slide inside this without friction. The first disc D1 is adiabatic and remaining discs are dithermal, thermally conducting. So first disc is adiabatic, means no heat can be exchanged from this cell to this cell or anywhere, and others are dithermal, means heat can be exchanged here. Now are thermally conducting. Each cell contains 1 mole of ideal monoatomic gas In each cell you have 1 mole of diatomic, it is diatomic. The disk can be very slightly and ideal. Okay, each cell contains 1 mole of ideal monatomic gas. It is monoatomic. Let the initial pressure, volume and temperature of each cell be P0, V0, T0 respectively. The gas in cell 1 is heated slowly until the temperature of the gas in cell Cn reaches final equilibrium temperature 4 T0. Find the volume of the first cell in terms of the number of cells and the initial volume V0. So what is happening here? Now you have this adiabatic wall and they all are diathermal walls, and there is 1 mole of gas in each container, and pressure, volume, temperature is P0, V0, T0 initially in each cell. Now what you did is you start heating this first cell, and now there will be increase in temperature of the remaining, and in the last the temperature of the Cn will become 4 T0. So you need to find that at that time when this temperature becomes 4 T0, what will the volume of this first cell. And now you will ask that if this wall is adiabatic, then how the temperature is going to increase here. So see, when you heat this container, the volume will increase. That will lead to the compression of this whole system because they are free to slide. So this whole thing will compress and temperature will rise. So that's how you will get the temperature increment. And when this cell is at 40 knot, you will see that this whole thing, beside this first cell, this whole thing will be at the 40 knot temperature. So we just divide this whole system into two parts. That is, first, this is your first disk, which is adiabatic. So this is at T naught, V naught, and the remaining is at T naught initially. This is the initial condition. Now total volume is first V naught, V naught, V naught, V naught. It will be N V naught. So N V naught minus this first cell will give you N minus 1 V naught. This is the volume of remaining one, and this is T naught. So this is the initial condition. Now you will see that this container is like a adiabatic condition is already there. Means this all walls are adiabatic, and there is whatever volume increase will from here, that will increase the temperature directly. So the final condition is, they say that this cell will become at the 40 node. So now this is the initial condition, final condition will be 40 node, and this volume changes to V2. So this system, we can see that this is changing from this condition to this condition, and this process is adiabatic. So we'll apply the condition of adiabatic, that is T1 V1 means TV gamma minus 1 equal to constant. So initially it's T naught, N minus 1 V naught, this is the volume, and final temperature is 40 naught and volume is V2. So just substitute the value and you will get your V2. Now you have find the V2 volume. Now you have V2, so how you can find the volume of this first cell? Means total value must remain constant, that will be NV naught. So NV naught minus this V2 will give you the volume of first cell, which is they asked that find the volume of the first cell in terms of the number of cells and the initial volume V naught. So that will be NV naught minus V2, so that will give you this value. So that's how you can calculate the value of the first volume. So you must know this process. So I hope or expecting that you understood this whole complete procedure, and if still you are having some doubts, you can put in the comment section. I will reply definitely. So I hope it is clear to you. So that's all for today. Thank you everyone.